We're going to discuss polar molecules now, and I have this example drawn up here, the HCl molecule, where hydrogen has a partial positive charge and chlorine has a partial negative charge because the electrons are being drawn down towards the chlorine end of the molecule. For polar molecules, one end of the molecule is slightly negative and the other end is slightly positive. It has been polarized. A dipolar molecule is a molecule with two poles, one negative and one positive, or that's the delta plus, that's the delta negative, that's the delta plus. So we know what makes a bond polar. It's the difference between the electronegativity of the atoms. What makes a molecule polar? Because a molecule can be more complicated. You have multiple atoms. Well, the first thing is that the molecule should have polar bonds. And the second thing is that the polar bonds must be unsymmetrical. Around the central atom. In other words, the molecule is lopsided in some way. Now, one thing that will automatically make a molecule lopsided is if we have a lone pair around the central atom. So that's one thing to look out for. Now let's look at these steps to determine if a molecule is polar. First thing we're going to do is we're going to draw the Lewis structure. Then we're going to determine the molecular geometry. We're going to look for lone pairs on the central atom, which is going to make it automatically polar with the geometries we have available. If there are polar bonds, are the polar bonds unsymmetrical in 3 dimensions around the molecule center? So let's take a look. Let's practice determining if molecules are polar or not. Remember, we're going to draw the Lewis structure, determine the molecular geometry, look for lone pairs, which means it's automatically polar if they're on the central atom. And then if there are polar bonds and they're unsymmetrical, then we know that it is polar. So, polar molecules are unsymmetrical. Or, to put it in something that may leave you with a stronger image, polar molecules are lopsided. So we're looking for lopsided molecules, and those are the polar ones. Let's start off with carbon monoxide, which has a total of 10 valence electrons. And we're going to draw the Lewis geometry. That's it right there. Oxygen is more polar than carbon, so the electrons are going to get drawn down towards the oxygen end of the molecule. This is a lopsided molecule. This is going to have a partial negative end, and this is going to have a partial positive end. So electrons pulled toward oxygen. And this means that this is indeed a polar molecule. So this one is polar. Now let's take a look at CO2. This has 16 valence electrons. First of all, we look for lone pairs on the central atom. There are none. So now we're going to look for polar bonds. And again, the carbon-oxygen bond is polar. So in each case, in each bond, electrons are being pulled away from carbon towards the oxygen. But what I want you to look at here is that the electrons are being drawn equally away from both sides. This is a linear molecule. So these poles are exactly 180 degrees apart from each other. So the polar bonds cancel each other out. So what this means is that this molecule is actually nonpolar because the molecule is symmetrical in 3 dimensions. Now let's try SO3, sulfur trioxide. And let's go ahead and draw this as it would appear in 3 dimensions, roughly. This is going to be a trigonal planar molecule with each one of the oxygens being at the corner of an equilateral triangle. So once again, trigonal planar. Going back up here, we don't have a lone pair on the central atom. So let's see if we have polar bonds. And if we take a look at the difference between sulfur and oxygen, there is a difference of 1 between sulfur and oxygen in terms of the electronegativity value. So let's highlight what's going on with the electrons being pulled towards the oxygens preferentially. What I want you to notice is each of these is being pulled at 120 degrees angle, and they're being pulled equally to the corners of an equilateral triangle. So once again, the polar bonds cancel. If you've had physics already, we would say these are vectors, and the vectors cancel. So, symmetrical molecule in terms of what's happening with the polar bonds. Since it's symmetrical, that means that it is nonpolar. Let's take a look at sulfur dioxide. And if we draw the Lewis structure for this one, we get a Lewis structure that looks like this. Now, at first glance, you might say, well, this is linear, and these two sulfur-oxygen bonds are canceling each other out. But remember, you've got the lone pair here. And so this lone pair is going to make this into a bent triatomic shape. So let's redraw it as bent triatomic. Oops, that's not even supposed to be there. Let me erase that. That's supposed to be a lone pair up there. We have a lone pair up here. Now, if we draw how the electrons are being pulled from the sulfur, we can see that the electrons are being withdrawn from the sulfur towards the oxygen. If we added these two together, we would see that this side of the atom has taken on a partial negative charge. This is lopsided. If you have a lopsided atom, or excuse me, lopsided molecule, that means that it is a polar molecule. So this one is a polar molecule.